Hello, my name is J.P. Laurenceau. I'm a faculty member in the Department of Psychological and Brain Sciences at the University of Delaware. And this webinar is going to be an introduction to intensive longitudinal methods, focusing on design and analysis of the data that come from these kinds of methods. This is part of an upcoming program called Data Science in the Social and Behavioral Sciences that's going to be held in the spring of 2021. And this is funded by the NSF as part of an institute called the Statistics and Applied Mathematical Sciences Institute. And it's a collaboration between Duke and NC State and University of North Carolina, Chapel Hill, and of course funded by NSF. This is one of about 6 or so webinars that are going to be held in preparation for this data science in the social and behavioral sciences program. So just a few acknowledgements here. Of course, want to acknowledge the support of SAMSI. And just so you know, one of the themes of the SAMSI that's going to be held in spring of 2021 is about sort of digital data and data that can be obtained from, I guess, dense data that can be obtained from a lot of sources such as smartphones and GPS devices, scraping of data from social media, and all of these eventually fall into the general area of time series, and then involving some kind of modeling that's akin to time series analysis. And there are going to be a couple of other themes as well. So I just want to thank my doctoral student, Emily Soriano, for help with these slides and getting feedback from Ken Boland, Peter Muka, and Adam Lilly. So a lot of the material, at least the first 2/3 of the material in this webinar, is going to come from the following book that I co-authored with Niall Bolger, who's a faculty member in social psychology over at Columbia University. So the main data example is going to come from this, as well as some of the background on the methods as well as the analysis. So let me give you an overview of the webinar that we'll be doing, and we're going to do it in 2 parts. So the first topic is we'll go over the goals of longitudinal research more generally, given that this is called a workshop on intensive longitudinal methods. At its basis, it's also about longitudinal methods. And then we'll do an overview of intensive longitudinal methods, as well as talk about the types of designs that would fall under this umbrella category, and then strengths of ILMs. Then we'll move to fundamental issues when it comes to modeling intensive longitudinal data. There are 5 that we think are pretty important to keep in mind, and so we'll review those. And then we'll spend some time covering the workhorse model for these kinds of data, called the multi-level model, but a form of multi-level modeling that is specific for longitudinal data. So we'll go through an example data set, and then talk about interpretation of the findings. And then we'll talk a little bit more about some analysis issues that can be challenging with these kinds of designs. One is missing data, another one is dealing with unequal intervals between the repeated measurements. And then we'll talk about some model assumptions and modeling extensions beyond what I would have covered earlier, and then some software options for being able to implement the example that was reviewed earlier, and some of the extensions and some exciting directions. And then I've provided some references and some readings at the end if you want to be able to follow up on this. So I hope everybody's ready for this. And where we'll start is talking more generally about the goals of longitudinal research. And I feel like a great quote from an annual review of psychology paper by Linda Collins in 2006 really crystallizes, or at least for me, what the goals of longitudinal research are. And she says, ideal longitudinal research is characterized by the seamless integration of a well-articulated theoretical model of change, an appropriate temporal design, and then a statistical model that's the operationalization of the theoretical model. So the idea is that those three pieces, when put together, provide an effective set of tools for being able to interrogate questions that are based in longitudinal designs and longitudinal data. So any kind of modeling of longitudinal data should keep this in mind. There's, you have to be driven by some theoretical notion of change. What will change look like? Is it linear? Is it curvilinear in a more of a quadratic shape, or is it asymptotic? Or is it cubic? Or does it follow some kind of other shape of change? And once you have some idea of what to expect, and a lot of our theories in social and behavioral sciences don't really tell us, right, about how long it might take X to have an impact on Y, or what is the shape of change of Y, some particular outcome. And then once you have that notion of what you might expect in terms of change and how long something affects something else, then you want to have an appropriate temporal design. So you want to be able to measure, in an ideal world, frequently when change is occurring in the outcome. And also you want to be able to, if you think that there's a causal influence of a time varying X on a time varying Y, then you want to be able to also assess at the peak of that time, of that relationship, when you expect that relationship to be at its strongest. And then once you have that design, where often, more assessments gives you more control and more options and less assessments, then you want to be able to have a statistical model that makes use of all the data, right? That talks about average effects, but that also allows for individuals to show their own effect that's different from the average. And then you want to be able to have parameters in that model that essentially parameterize the hypotheses that might be driven or that be drawn from the theoretical model. So longitudinal methods generally is a methodology, right, that involves repeated time-ordered observations of some unit, some entity, with the goal of identifying processes and causes. Right, this is the lifespan development view of longitudinal methods from Baltus and Nesselrode. Now, this webinar is about intensive longitudinal methods, which are basically an extension of longitudinal methods more generally, except in this situation, the repeated measurements are often much more densely spaced than is typical, in the standard longitudinal design, at least in the behavioral and social sciences. So we consider intensive longitudinal methods as an umbrella term that covers a lot of different kinds of designs, which we'll get into right now. The philosophy behind intensive longitudinal methods can be captured by this quote from Gordon Allport, the personologist, personality psychologist. Psychology needs to concern itself with life as it's lived. And I guess more generally, I might substitute psychology with behavioral and social sciences need to concern itself with life as it's lived. So that's, the general sort of philosophy behind these kinds of methods, where we want to be able to study individuals and understand processes that individuals experience. And individuals experience these processes in their everyday lives. And so we need to also be able to capture that process, or those processes or outcomes that we're interested in examining for individuals in the very environment in which they're living. So that's the idea behind intensive longitudinal methods, is to try to be able to capture individual processes or processes on individuals, measuring enough time points to adequately capture that process, and then do it in an ecologically valid context, which reflects people's everyday lives. So a more formal definition of intensive longitudinal methods is the following. So a study that is an intensive longitudinal one is one that has enough repeated measurements to model a distinct change process for each individual. Right, so the idea is that we want to measure enough times for each individual to be able to capture adequately some change process that's under investigation. So with this focus on the individual, within individual or within person variability is key. We're really going to be interested in within person variability in our outcome, as well as within person variability in our key predictor or predictors, and being able to look at links between those two. The time scale for these repeated measurements in intensive longitudinal designs is more on the order of minutes or hours or days and even weeks, rather than months and years, which are often panel designs. Classic panel designs might be 6 months assessments or yearly assessments over a number of years. And we see that as not falling under an ILM umbrella, because the idea is that you want to be able to capture everyday life. And a way to do that is to take numerous snapshots in the moment, or across moments, or across days in the life of some individuals or a dyad. And in the social and behavioral sciences, at first, they were used to understand people's thoughts, feelings, and behaviors in the situations in which people find themselves, right? But more recently, with the advent of electronic forms of collection of data, some of which happen automatically and passively in people's lives, it's also used to, these designs can also be used to study other kinds of phenomenon in which people find themselves in. And we'll talk a little bit more about that in another slide or two. So what does it mean for us to study some behavior, thoughts, or feelings in situ? Well, the idea here is that laboratory studies are very powerful tools. They're great for testing theory, where you can control an environment and manipulate one variable at a time, and then be able to see and measure the resulting effect of that manipulation on an outcome. However, there are a lot of things that we want to study where there are essentially practical or ethical or ecological limitations in the use of laboratory designs. And so we actually can't manipulate that we're interested in studying. So that's where intensive longitudinal methods come in and can be a really powerful set of tools, because we can use these methods to try to document what actually happens in people's lives. And sometimes that extends from the laboratory, but sometimes there are experiences in life that you won't see in the laboratory or are harder to replicate in the laboratory. So a conclusion might be that laboratory studies document what can happen, where you can study some phenomenon and try to understand the limits of the phenomenon in a controlled environment. But ILMs are used to document what actually does happen in the everyday life of individuals. So here's a slide from a nice Perspectives in Psychological Science paper where they show the number of publications using the term experience sampling or ambulatory assessment or ecological momentary assessment or daily diary. These are all terms that I would argue fall under the term or under the umbrella of intensive longitudinal data, as is indicated here at the bottom of this figure caption. So we can see that both PsycInfo and PubMed databases show a pretty nice growth, an exponential growth perhaps even, in the use of these methods in the social and behavioral sciences, and maybe even in the biomedical sciences. And while this graph, the axis on X only goes out to 2015, I believe that this trend has continued, perhaps leading toward an asymptote, but I believe that we're going to continue to see more and more of these kinds of designs out there in the literature. Part of the reason why is because we are, with the advent of lots of technologies, increasing our ability to be able to observe behavior broadly defined. And so, you know, smartphones are something that everybody carries in their pockets these days. And smartphones are used in these kinds of designs to be able to, you know, push a request for a survey or a set of items to be responded to by a participant at particular times throughout the day. And then people can report on their momentary thoughts, their momentary affect, the context in which they find themselves. But nowadays, there are ways of collecting lots and lots more data of different kinds from individuals. So everything from smartwatches and these activity bands that can count physical activity, that basically are triaxial accelerometers of some sort that can give you information about physical activity, can give you information about intensity of the activity, can also even give you information about sleep, which can be inferred from the absence of activity. And these kinds of sensors are being built into bands, into shoes. Now there are ways of being able to get lots of physiological assessments in an ambulatory way. And even a cool version is a smart surfboard that has GPS built into it. But GPS is also becoming a source, and that's part of everybody's phones, location information. And of course, everybody's cell phones or smartphones also have built into it, if you didn't know this, a triaxial accelerometer, again, giving you information about physical activity in a passive, ongoing way. So these will create incredibly dense data streams on individuals. And this is part of the reason why I think these kinds of data are going to be rich sources, and they are rich sources for a lot of research today, and they're going to be rich sources in the future. So what are some of the strengths of intensive longitudinal designs? There are several. They're not a panacea, but there are several, I believe. that are worth noting. So one is that we can actually document certain processes that as they actually occur in everyday life. So ecological validity for these kinds of designs are very high. It's very high. We can also examine how varying contexts or situations individuals find themselves in might be associated or potentially influence daily affect or cognition or behavior. Another strength is that we can minimize retrospective bias. So the idea here is if you ask people, how are you feeling right now? What's your level of happiness? What's your level of frustration or anxiety at this moment? What kind of thoughts are you having? Who are you with? What exactly are you doing right now? You know, these kinds of questions, at least when asked in a momentary way, pretty much minimize or can remove retrospective bias. So if you're really trying to understand a class of behaviors or a class of emotional experiences and how they're experienced in a moment-to-moment way, this is a great design to be able to do that with. And of course, people are notoriously bad reporters of their own behavior or thoughts or affect. And so catching them in the moment gives you a better chance of getting a sense of what actually is going on. Another important strength of this kind of design is that there's a focus on within-person variability or within-person changes and differentiating that from between-person differences. And so this gets back to this focus on individuals and within-person variability. And we want to be able to examine relationships between an X and a Y that vary within person, but not have that relationship be contaminated by the fact that people will differ from each other on X and people will differ from each other on Y, which is a between-person association. So this difference between within-person associations and between-person associations is going to be an important one that we'll see later in the webinar. And there'll be an example of this later on. Another strength is that you can complement these kind of daily process methods and have them be part of larger macro level longitudinal designs. Right? So you can actually have a panel design where you might take multiple bursts of multiple days over the course of a longer period of time in a panel design. And what's exciting about that kind of design is that not only does it allow you to look at and study some process as it unfolds in everyday life, but you can even look at how the process itself may change over time. So I see that as a strength of these intensive longitudinal when it's embedded and coupled with a more standard panel longitudinal design. The first strength that I mentioned was really about studying thoughts, feelings, behaviors in people's everyday lives, and it, speaks to the issue of external validity, right? Which is about about having findings that generalize across people, across places, across time. Okay? And more specifically, ecological validity speaks to to research findings that will generalize to people's everyday lives. And that's really what this design is all about, or these kinds of designs are all about, the kinds of data that come from these designs. Okay. And early work by Brunswick talked about this concept of a representative design, that is representative sampling of situations, where he was interested in matching the range and the characteristic distribution of conditions and condition combinations presented in experimental design to those presented in the real world. So he was really interested in real world phenomenon and sampling of real world situations. So this 2x2 table is an interesting way of depicting a crossing of two dimensions that I think intensive longitudinal methods and the different kinds of designs can find themselves in. So across the top here, there's laboratory, and then there's real world. And going down here is subjective data versus objective data. And when we do a crossing, we get this 2x2, where intensive longitudinal methods can involve subjective data that's obtained in a laboratory setting, and that's a possibility, right? Or that we can assess, we can get measures of subjective data in a laboratory setting, right? But we can also get those subjective data from people as they ambulate and live in the real world. And that's really where I think intensive longitudinal designs find themselves. In the laboratory, we can obtain objective measures, like in this example here, there's a pricking of blood and maybe trying to get a measure of blood glucose, right? And that can be done under particular settings. Other kinds of objective measurements can be taken in the lab, like cortisol assessments or other kind of hormonal assessments, while people are experiencing particular kinds of paradigms. But you can also get physiological assessments as people experience the vicissitudes of life, basically, right? As they find themselves going in and out of different situations, speaking with different people, being in work and transitioning from work to home or back again. And this is an example here of a glucose monitor, a continuous glucose monitor, where there's a sensor that's placed on people's tummies, and then there's a receiver that communicates with the sensor and gets measurements of blood glucose every 5 minutes, right? Again, objective data, but obtained in the real world. So there are two types of prototypical research questions that can be leveraged to try to answer with using these kinds of designs, these intensive longitudinal designs. The first is where the focus is on time as the primary predictor. How does a typical person change over time, and how much do people differ from one another in that change? So the idea here is that we want to try to characterize some kind of functional form of time for individuals. Okay. In this workshop, we'll focus on linear change, but it doesn't have to be. It can be more complex than linear. It could be some form of nonlinear change. And a lot of nonlinear change can be approximated with linear or additive models. So we characterize the functional form of change for individual. And then we try to see how much do people differ from one another in that change. So we allow for individual differences in the parameters of that functional form of change. And then once we have individual differences in those parameters that capture the functional form of change, we can then try to explain those individual differences with variables that are person-level variables, variables that vary between people. So that's one kind of question. And that's essentially a form of growth curve modeling. Some of you might be familiar with growth curve modeling. This is essentially what that is. The second kind of question, though, is more about process. And so we want to be able to characterize the within-person process for the typical person, And when I say process, what I mean by that is we're interested in how some time varying X is associated with or co-varies with some time varying Y. And so that association is what we're referring to here as a within-person process. And what is that within-person process for the typical person? And then how do people differ from each other in these processes? So I have a parallel question from what we asked before. But here, the key predictor is not so much time, but it's a time varying X. And time is what allows X to unfold, and it's what allows Y to unfold. Hopefully these will come more to life when we look at an example. So here's the first question, where we're interested in the functional form of within-person change and how do people differ in that change. So let's say we have 4 individuals here, A, B, C, and D. And let's say that these are men who are in a marital therapy where they're receiving weekly marital therapy over the course of 16 weeks. And we're assessing their intimacy on an outcome ranging from 0 to 100. Okay. And so for persons A and B, we can see that over the course of the 16 weeks, they're each increasing over time. These distributions here on the y-axis give you an idea of the spread of their scores, the variability, the amount of within-person variability in their scores. But here we're really interested in the shape of change over time and trying to find a good functional form. Right? C and D, they have less within-person variability, but again, that's not so much of the interest. The interest is about how that variability in the outcome changes over time. And people are, these people, C and D, are not changing, right? So they're varying in where they start. They're varying, or at least there's some variability in whether they go up or whether they stay flat. And this thick line here represents the trajectory for the typical person, starting at about this point and going up some amount. Now, this typical person is essentially represents the average of all 4 individuals. And if I were to tell you that, let's say these 2 individuals were in an active treatment, focusing on improving their intimacy with their partners, and these 2 people were put into the weightless control condition, this would be a great discriminator of the individual differences in change over time for these 4 individuals. Right? However, if I didn't have that between-person predictor, I would have this collection of 4 individuals, and I'd have this typical person that really doesn't capture anybody in terms of the amount of change over time. Right? If I knew that these people were in one group and in another, I would have a typical trajectory for the people in the therapy group and I'd have another trajectory for the typical people in the control group. But across all 4 of them, this typical person, at least in this egregious example here, doesn't represent anybody. And that's something to be aware of when we're looking at averages. That sometimes averages may not represent any particular people in your sample, and you want to make sure that there are people that follow or that are representative of the typical person, in addition to the people who might be different from the typical person. But the idea here is that we're looking at change over time, and time is the key within-person predictor. Let's contrast that to the within-person process question, where let's say we have here 4 individuals, They don't have to be the same 4 individuals. It could be a different set of 4 individuals. And in this case, we have days on the x-axis, and we have intimacy rated from 0 to 100 on the y-axis. And we have this little triangle here that represents a couple's night out, right? So the idea here is that people will vary on a day-to-day basis on whether or not they go on a date night with their partner. And we're also tracking intimacy on a day-to-day basis for these 4 individuals. And what I hope you can see here is that there seems to be a tendency for when there is a date night, there tends to be an increased level of intimacy compared to when there aren't date nights, right? So these date nights, there tends to be an increase, and that seems to be the case for all individuals. For all individuals, except individuals A and B, the bump up, if you will, is much bigger in intimacy on the date nights compared to the non-date night days. Whereas for people C and D, it's a lot smaller, the bump up. So overall, there's we might say that there's an effect, at least an association, depending, on the design, an association between having a couple's night out and having a higher level of intimacy. But that association varies across the 4 individuals, where the bump up is a lot smaller for C and D, but the bump up in intimacy is a lot larger for A and B. Right? Again, we're in a situation where we might be able to model these individual differences and what's different about persons A and B versus C and D. Maybe it's that persons A and B don't have kids or don't have young kids in the home, but persons C and D do. That might be a between person factor that explains this variability. The idea here is that the key predictor is not necessarily time, at least in terms of a hypothesis about the effect of a couple's night out as a time varying predictor. But it's time that allows the couple's night out to happen or not. And it's time that allows intimacy to fluctuate and to be higher versus lower, depending on the day. And so we're interested in capturing that process, characterizing what it is for the typical person, and allowing individual differences in that process, and then hopefully being able to explain those individual differences. Okay. How do we compare intensive longitudinal methods more generally to the more general, longitudinal designs, right? These are some dimensions in which they differ. And some of these distinctions are fuzzy, I have to admit. They're not, strict differences, but I think hopefully you'll see that that we can make some fuzzy, at least, distinctions between these 2 kinds of longitudinal designs. So while the traditional longitudinal design is often a handful of time points over time, intensive longitudinal designs have 10 to 20 and even more. There's some designs, intensive longitudinal designs, that have hundreds of time points. Another difference is the density of the assessment, right? For traditional longitudinal designs, it tends to be on the order of weeks or months or years in terms of the separation between the time points, whereas for intensive longitudinal, they're on the order of minutes or hours or days. The assessment timescale is also tends to be different, where traditional longitudinal designs typically look at global measures, or if you're taking some kind of subjective assessment from the participant, you're asking them about their experience or their mood over the past month, for example, whereas the assessment timescale for intensive longitudinal is more momentary or where there's minimal introspection or retrospection, excuse me, such as, did you have a conflict with your partner today? Yes or no? Did your partner support you in some emotional way today? Yes or no? And then the typical goal of traditional longitudinal designs is to model outcomes, right? And is to try to predict outcomes. Whereas really what the focus of intensive longitudinal design is to understand processes and to model those processes. There are different sampling approaches for intensive longitudinal methods. And I'll go through them here. So the first is an interval contingent design. So that's where basically the participant reports or provides data on a particular interval, like a daily diary, where they're going to give you reports at the end of the evening for, let's say, 28 consecutive days, right? Or maybe give you reports in the morning over those same consecutive days. There's the single signal contingent design. And an example of that is the so-called experience sampling method, ESM. A very similar methodology that you find often in health psychology or behavioral medicine is EMA, which stands for ecological momentary assessment. But the idea there is that people carry around a device, often it's their smartphone, and then they're pinged or they're notified to respond to a set of questions or to provide information in response to a signal. And they're signaled, at least in the experience sampling method, they're signaled often randomly throughout the day. And so the response and the data collection is contingent on that signal. There's event contingent designs where basically you're interested in studying a class of behaviors or a class of situations that people find themselves in. And so there's a particular event that is characteristic of that class, and you want people to give you reports of on that particular event, or what happened right before, what happened during it, what happened right after. So, sleep actigraphy might be an example of that, where, sleep, you can use some actigraphy devices where you basically press a button on the device that's on your wrist to tell the device that this is when you're intending to go to sleep. And then, the triaxial accelerometers record movement during that period of time, and then you press the button again when you've woken up. Right? So the event there is sleep, and you're getting very detailed information about that class of events or behaviors. And then more recently, with the advent of technology, there are so-called device contingent designs, where basically a device based on some kind of algorithm, or it could be in a continuous way, is assessing something like, for example, physiology, right? So let's say a blood pressure monitor, where the device goes off at random periods of time throughout the day. Or another example of a device contingent design might be where you have a recording of physiology or ambulatory physiology that's going on throughout the day, let's say heart rate. And when the heart rate goes above a certain number, then there's an algorithm that picks that up and then pushes a signal to the smartphone to ask the participant to tell you exactly what are they doing at that moment, or where are they, or who are they with. Okay. And here are the characteristics of these different kinds of sampling approaches. Okay. These are usually equal intervals, and the same across participants, the interval contingent, the signal contingent. Researcher determines the interval, and it's usually the same across participants. Event contingent, they're unequal intervals. And having missing data at random may be less tenable, and we'll talk a little bit later about missing data. And often the number of assessments differs across individuals because it depends on the event and when the event occurs for people. And the device contingent, they're also usually unequal intervals. There's some algorithm or rule that triggers when the assessments occur, and this can be different often across individuals. Now, a fifth kind is a combination, right? You can combine these approaches in some way. And that actually leads to some really interesting kinds of designs. So for example, and this reflects a study that we're involved in now, we have diabetic patients wearing continuous glucose monitors that give assessments of blood glucose every 5 minutes continuously 24 hours a day for 7 days. But also, in addition to that, and that's happening passively, we're also using an experience sampling method where we're asking people at particular signals to respond to a set of questions that have to do with stress, that have to do with the level of or the nature of interactions that they may be having with their partners, that have to do with what kinds of activities they're engaging in. Okay. And so these kinds of combination designs can open the door to some really interesting ways of answering questions that really couldn't, be answered solely with any one of these designs. Okay. There's the concept of sampling theory that becomes relevant here, because you can have interval sampling, and as it says here, the length of the interval should be much longer than the length of the behavior of interest, so that multiple occurrences can occur within any interval. So you want to keep that in mind when you're picking the intervals that you're selecting, depending on the particular kind of intensive longitudinal design. And let's compare that to momentary sampling, where the intervals between the assessments they should be relatively short relative to the rate of change of the phenomenon of interest, right? So basically, you want to be able to measure multiple times as the phenomenon is changing, because if you measure before and after, you won't be able to really characterize the change or the process of change of that phenomenon. Okay, let me get to covering 5 guidelines for modeling intensive longitudinal data. And these apply to actually all longitudinal data, but they're particularly relevant for intensive designs. And basically, here are the 5 guidelines. First, we want to allow for random effects. That is, that we want to allow subjects to differ from one another in within-person processes. And I'll show you an example of each of these in turn. So remember this example here. The typical person represents the average, or the fixed effect, as is often called. But we want to allow there to be individual differences or random effects, between person random effects, in where people start at the start of therapy, as well as individual differences in how quickly people go up, in this case, linear change. Right? So we want, in this kind of example and these kinds of designs, to allow there to be random effects And this would be the case for, the question of functional form, but it would also be the case for the question of process as well, that we would want to allow the processes to vary from person to person. Second guideline, even if temporal change per se is not of direct interest in your study, we think it's really important to take the influence of time into account. So you should have time as an explicit factor in any model of interest. And in particular, there are two ways to have time as part of the model. Okay, the first is to actually have time as a predictor. So here's an example where we have some outcome Y, we have an outcome X, and it's measured over 5 time points. And we could even think about this as being for an individual. And the X outcome is in the dotted line, the Y outcome is in the solid line. And what this drawing is trying to depict is that there's a correlation between X and Y, because as X goes up, Y goes up, right? But this correlation is completely due to time. Basically, time is a confounder of this association between Y that varies over time and X that varies over time, right? And so if you included time in the model, you would see that the association between X and Y would be essentially 0, right? And so you want to be able to include time because it's often a one explanation for why a time varying X and a time varying Y might be related to each other. They just may be increasing monotonically or decreasing monotonically over time. And we want to be able to account for that. So here time is included you want to include time as a predictor. But another way of modeling time is in the residuals. Okay, and in particular, the residuals at the lower level, or at the level 1, if you will, or the within person residuals, because it's within person variability that really is the emphasis here, or the focus. So let's think of these data here representing an individual where they're assessed over time on some outcome, and the residuals you can envision as being like little distances from each data point to the line. And the pattern here is meant to represent a random pattern where autocorrelation in the residuals would be 0. That is, the distance of the residual at one time point doesn't say anything about the distance of the residual at the next time point. Right? Whereas in this panel here below, there's this undulating pattern of the residuals that is represented a very, very high autocorrelation. So basically what happens is if the next residual goes below the line, then the residual tends to stay below. And if it goes above the line, it tends to stay above. And if it goes below, it tends to stay below, right? That kind of undulating pattern, smooth undulating pattern, is characteristic of high positive autocorrelation in residuals. So what might cause this kind of a situation? Well, one thing I can say is that the more densely assessed your outcomes are, and your outcomes are in particular, the more likely you are to see this kind of positive autocorrelation in the residuals. Let's think of this as like a daily diary study, right? And let's say we were assessing mood in some way, right? And so what might cause these kinds of this kind of situation might be where, let's say we knew that this time point was Sunday, and then we go to Monday and mood is relatively low. Monday stays low, Tuesday, Wednesday, Thursday, until the weekend. And then in the weekend, it's higher and it stays higher until you start getting back to the weekdays. So here, weekday weekend effects, or actually day of the week effects, would be explaining this pattern. And if you didn't have a weekend, weekday, or day of the week factor in your model or predictor in your model, you would then, see this kind of autocorrelation. And so you can think of autocorrelation in the residuals as a placeholder for time-varying predictors that you have not yet included in your model. And another example, just to give you another example that comes to mind, is, let's say we knew that during these days, this is when a person was sick, and when people get a cold, colds tend to linger. So the cold lingers and has an effect on mood that lasts a few days until the person, gets out of the cold and feels better. And so their mood then elevates and, it stays higher. So cold versus not having a cold on a particular day would be a time-varying predictor that could explain this kind of a pattern. But again, if you didn't include it in your model, what will result is this pattern of residuals. Now, why do we care about having then a parameter that captures this? It's well known in the time series literature that in the presence of autocorrelated residuals, you get biased standard errors, right? And standard errors affect your inferences. And it's often the case that you end up having smaller standard errors than you otherwise would in the presence of autocorrelation, and that'll lead to type 1 errors. So in this case, you need to allow for level 1 autocorrelations in the model. This is another way of incorporating time, but in this case, this is in the residual. Okay, the third guideline, specify the appropriate number of independent units. So this has to do with degrees of freedom. Okay? And essentially, the total number of observations, which is the number of people times time points, those observations are not independent from each other. They're not independently sampled. And essentially, you want to treat the upper level units as independently sampled. Okay? So this is a units of analysis issue. So let's think of this sort of, basic data set here where we have 5 individuals. Each individual is measured 5 times. We have an X that is measured for individual 1 over 5 times, and this X can vary both within and between person. And we have a Y that's measured over the 5 times for each individual, and the Y can vary within and between person. And then we have so-called W variables. And the W variable is a variable that is time invariant. So the value of W stays consistent across the 5 time points for each individual. So X is a time varying predictor, W is a time invariant predictor. But when it comes to thinking about units of analysis and basically degrees of freedom, should we be thinking about the number of people at one extreme, which would be 5, right? Or the number of observations, which is the number of people times 5, which would be 25 observations. So should degrees of freedom be based on 5, or should it be based on 25 in this kind of design or repeated measures design? And essentially, the bottom line is that basing degrees of freedom for your tests of significance, if you're using t-tests, which is often the case for testing regression coefficients, you want to be able to use the upper level number of units. In this case, the number of people is much more defensible than basing your inference tests in terms of degrees of freedom on the number of people. The fourth guideline is it's important to distinguish the between person and within person levels of analysis. And basically, not distinguishing these can lead to confounding. And that's because the relationship between two variables that vary both within and between person can be different at the within person level versus the between person level. And they can be different not only in the size or the magnitude of the relationship, but they can also differ in sign. There's nothing, they need not be the same size or sign. And ignoring these two levels will lead you to some biased conclusions. So the idea here is that we want to distinguish differences between people versus differences within people. And the idea is that between person differences reflect the fact that people differ from each other. You have a group of individuals, individuals differ from each other on whatever attribute you may measure. But if you also measured that same attribute over time, and if there's within person variability, that reflects the fact that people can differ across time, right? Basically, people differ from themselves over time. And some variables will contain both of these kinds of variability. And they'll be part of the total variance of this variable. So you need to carefully distinguish these levels of variability, essentially, or variability at these different levels. And multi-level modeling, which is, again, the workhorse model for these kinds of data, distinguishes within and between person variability automatically in the outcome, but it doesn't do so automatically for the predictor. It really depends on the particular software package that you're using. And I think it'd be safe to say that most packages do not do this kind of distinction for the predictor. You need to know that your predictor is varying only within person or only varying between person, or if it's varying both, you're going to have to do some kind of separation. You're going to have to take into account the fact that different people are going to have different mean levels on X. And you need to take that into account in some way. So multi-level modeling doesn't automatically do that for the predictor. Here's an example of where the relationship between X and Y might exist, but it's different at each level of analysis. So in this example, on the X-axis is amount of exercise, let's say, and on the Y-axis is blood pressure. And these are 5 individuals, ID 1 through 5. And it's not shown here, but imagine that we have, a cloud of data points around the regression lines here for each of these 5 individuals. Right? And for each of these individuals, when that individual, whether it's person 5, 4, 3, 2, or 1, when that individual exercises more, their blood pressure goes up. Hopefully that makes sense. For any one of you who are watching this, if you went from a sedentary state to a state where you're doing jumping jacks for 90 seconds, right, your blood pressure would go up correspondingly, depending on the amount or degree or intensity of the exercise that you're engaging in, right? So within person, the relationship between exercise and blood pressure is positive. But now let's think about the between person. Let's say if we got each of the 5 people's average exercise level and average blood pressure, which would essentially be, right here in the middle of the line here for each person. And those were the data points, because there, the only variability is that this point differs from this person's point, differs from this person's point, and so on. So the between person variability, and if you were to try to capture an ellipse around that or draw a line through those data points, the averages, that line would be like this, indicating that that more exercise is associated with lower blood pressure. So between persons, right, people who exercise more tend to have lower blood pressure, right? And I think the process that leads to that association between person is completely and totally different than the one that leads to the association between exercise and blood pressure within person being positive, right? One is a habituation process where people who exercise more over time, that the body sort of habituates and builds up tolerance and builds up strength, and therefore blood pressure tends to be lower. Whereas within person, that's a totally different process. When you go from a low intensity activity state to a high one, your blood pressure is going to go up. It has to, because that's how you actually move, right? Is for your blood to circulate quickly to the muscles to be able to get you to move. And so if you asked me what's the relationship between exercise and blood pressure, you'd really have to clarify, do you want to know that relationship, what it's like at the within person level of analysis or at the between person level of analysis? Because in this egregious example here, and I picked this, to make it so that not only can the size of the relationships at each of these levels of analysis be different, here the sign of the relationship is completely opposite. And not distinguishing within person from between person variability in exercise and in blood pressure would lead you to have some blended coefficient that represents neither, right? That represents the relationship at neither level. So distinguishing these two will be important. I'm not saying that you're always going to find this kind of egregious difference where they're in opposite signs, but sometimes for some phenomenon, it's really driven by the within person association and not be the between. And other times, for another different phenomenon, it might be the between person association that's really driving the link, and there isn't much of a within person association. Okay. Another comment on this issue is that between person associations that are based on observational data, where there isn't a manipulated X, they're prone to alternative explanations by a whole host of between person confounders, right? So the idea here is that if you find two variables related at the between person level, there can be numerous other between person variables that would explain that association. But a within person association cannot be explained by a between person variable or a variable that's stable for the person, or a situation that's stable for the person. That cannot be a confounder. A between person predictor or a person predictor cannot be a confounder of a within person association. And that within person association is what we're really after if we were to collect longitudinal data on individuals. The last guideline, choose interpretable 0 points for your independent variables. This is also known as centering, essentially, choosing the 0 point for your predictors. Centering generally involves subtracting some value from a variable which changes the 0 point on the variable. And in multi-level data or in intensive longitudinal data where you have repeated measurements measured on a bunch of individuals or units, they're going to be, for the variables that vary at both levels of analysis, there are going to be two kinds of centering. There's going to be centering across all individuals and all of the repeated measurements, which would be grand mean centering. But we can also think of person mean centering, where each person will have a different average level on that variable. And even if they vary within person, the means can vary from person to person. Okay. So those are the two kinds of centering that exist for these kinds of data. Now, generally with centering, the idea with centering is that it's generally not a good idea to just leave your predictors, your X's, whether it's the time varying X's or your time invariant W's. It's not a good idea to just leave them in their raw form unless they have true zeros that you understand, right? So we'll show some examples of this later in the data example, where we might be centering some variables and leaving some variables in the raw form, but we do it purposely. Time is also a predictor that you should have a good idea of what the 0 point is, right? So if you have an outcome that is systematically changing over time, as in a growth context where you're expecting a monotonic increase or decrease or some kind of functional form, often it's a good idea to put 0 at the beginning, right, at the initial time point, so that then you can interpret the intercept at that initial time point, and then the parameters of the functional form will show you how the individual changes from that initial time point. When you have a context where the growth trajectories are pretty much flat and there's really nothing much happening over time, and perhaps you're not even really interested in time as the key predictor, you might be interested in a time varying covariate as the key predictor, then putting 0 in the middle of time could be a good option. Okay. If you're in a situation where there's an outcome that you're tracking and the participants are headed towards something at the end of the study, like tracking patients leading up to surgery or transplant, or let's say tracking medical students as they're tracking anxiety of medical students as they're approaching the MCAT, for example, where the MCAT is at the end of the daily recording period. Well, it could be useful to put time at the end, at the last time point in that kind of a situation. So moving to talking about data, intensive longitudinal data that result from these kinds of designs, they're a special case of multi-level data. Right? And multi-level analysis, modeling for multi-level data go by a lot of different names. You might be familiar with some of these different names, depending on what field the particular researcher is coming from, biostatistics or sociology, education, or psychology, political science. But the idea is that all of these types of models, they are very similar at their heart. But what's different about longitudinal data when you're using a multi-level model? Well, this might be obvious, but really the major issue here is that the data are not just nested, as in kids in classrooms, the canonical example from education, like an organizational nesting, right? But the data are nested in a particular order, and the order is a temporal one, right? Basically, the repeated measurements might be nested in individuals, but observation 1 always becomes before observation 2, and 2 before 3, and so on and so forth, right? And so in the canonical kids in classrooms example, or other kinds of nested data structures, the ordering doesn't matter. Like, it doesn't matter who's kid 1, who's kid 2, who's kid 3 in classroom 1. So this kind of strict ordering is not, really a feature of multi-level modeling of those kinds of data. And when we have time points of observations that are fixed across time and across subjects, let's say a daily diary design where everybody's going to be assessed for 28 consecutive days on some outcome, then we can treat time and conceptualize time as crossed and not just nested. And that's because everybody in that daily diary study has a day 1, and everybody has a day 2 and a day 3, and those days have a common meaning across all the participants. Right? So longitudinal designs, while they can be analyzed using multi-level models, they're a particular kind of multi-level context where the ordering of time matters, and time needs to be part of the model. And as I mentioned before, there are 2 ways. One as an explicit predictor, and the other way would be also reflected in the residuals of the model, the lower level residuals. So here's this minimal data set that I mentioned to you before, right? So we need to conceive of basically data sets in this kind of structure, which is called the long structure, where basically the repeated measurements are different rows. And so the more time points you have, the more rows each participant will have. Okay. And that's to be contrasted with the wide format, where basically it's a format that you would see in the so-called MANOVA models, or repeated measures ANOVA models, where time represents different columns in the data set on a variable that's measured repeatedly over time. So this is the long format, and this is going to be the most useful format for the majority of analyses of intensive longitudinal data. So we're going to see an example where we'll have these variables. We'll have ID, we'll have time, we'll have a time varying X, or variable that varies both within a predictor that varies both within person and between person. We'll have an outcome that also varies both within person and between person, and we'll have a W variable that only varies between person. Okay, so we're at the point now in the workshop, or the webinar, where we're going to be going into the basics of multi-level modeling. And I think this would be a good time to take a break for now. And so this is the end of part 1, and we will pick up with, you can pick up with part 2 if you're interested in seeing the rest of the webinar. Thanks for attending, and hopefully we'll see you soon at the part 2 of this webinar.